is either 0 or 1. In the decimal scale, we have the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And then, beyond that, we carry a 1 to the next place to the left, and the first digit goes back to 0 and starts again. But in the binary scale, the numbers are represented like this. We can represent the numbers 0 and 1 by a single digit, but then when we want to go beyond that, we have to carry 1 place to the left. So the number 2 is represented by 1, followed by 0. The right-hand digit goes back to 0. For 3, the right-hand digit goes up to 1 again, and then for 4, we have to carry another digit over to the left, and so we get 1, 0, 0, and then we start counting the right-hand digits up again. 5 is 101, 6 is 110, and so on. Let's watch it go a little further. For 8, we have to carry another digit to the left. 9, 10, 11, and so on, we get by counting up in the right-hand digits again in this way. So storing a number, a binary number, is easy. For example, a magnetic core can magnetize one way, like that, could represent the digit 0, and a core magnetized the other way could represent the digit 1. So that if we wanted to represent a number such as, say, 26, which needs 5 binary digits, we could use 5 magnetic cores, each one magnetized in the direction corresponding to the digit that it represents. 1 represented by anti-clockwise magnetization, and 0 by clockwise magnetization. Well, so much for storage. Now, using whatever form of coding we have for the numbers, we need an arithmetical unit that will add, subtract, and so forth. In other words, produce the representation of numbers that are the sum or the difference of other given numbers. Now, this part of the machine is also made of small circuit elements, each doing one very simple logical job. Without going into the precise arrangement of the valves or transistors inside, we can simply draw each element in this sort of schematic way. Here we have an element which may perhaps be made of 2 or 3 transistors and some other components. Never mind how it's made. It does a simple task, which is to combine 2 incoming streams of pulses on 2 different lines to give an output pulse stream. And the rule that it follows is that it gives an output pulse if it gets a pulse on both of the incoming lines, but not otherwise. So that a pulse on the top line, for example, does not itself produce an output. A pulse on the bottom line does not produce an output. But if we get a pulse on the both lines together, then we get a pulse out on the right. There we have another circuit element which does a similar job, except that in this case we get an output pulse if either or both of the incoming lines carries a pulse. A pulse on the top line gives us an output. A pulse on the bottom line gives us an output. Or a pulse on them both together will also give us an output signal. This one at the bottom here follows similar rules. We get an output with a signal coming in on either or both of the incoming lines. But it also has a third input line coming at the bottom here, represented by this little circle, which means that this will prevent a pulse coming out regardless of what may be coming in on the left. So that so long as there is a pulse coming in on this special input called an inhibition, it will prevent an output pulse no matter what may be coming in on the lines on the left. Well, those are just some of the simple circuit elements that are used for doing the operations of arithmetic. And we can make up little assemblies of these elements to do the various jobs that need to be done inside a computer. For example, here is a circuit that will add together 2 numbers, each represented in binary form. The numbers come in on those 2 lines on the left, the digits of each number in succession along its line, and the sum comes out with its digits in succession, one after another, along this line at the bottom. And in fact, there is a carryover, of course, from each stage of the addition to the next, and this is conveyed by the signal line going up to the top of the screen, back to the left, through that triangle which represents a delaying element, so that it arrives at the right time to be combined with the 2 digits in the next stage of the addition. In fact, the machine does its additions from right to left. The first 2 digits to arrive are the 2 on the right, which are combined together. Any carry from those is fed back and combined with the next stage of the calculation. Well, I won't try to explain in detail how it works, but in fact, each one of those elements there simply does the job that I explained just now with those little diagrams, and the effect of the whole assembly is to do this process of adding binary numbers. Of course, a real arithmetical unit is a good deal more complicated than that. It not only has to do addition, it also has to do subtraction, multiplication, and so on. Those then are the 2 main parts of a computer, the store and the arithmetical unit, both capable of working at enormous speeds, but a computer needs a few other things as well. It needs a way of putting in the new data, the numbers that are given as the starting point of a calculation. They may not be very many, even for a long calculation. But since the arithmetic is so fast, we don't want to take too long just to put in a few numbers. So we get them all prepared beforehand in a special form so that the machine can read them quickly. There are 2 forms that are commonly used. Here's one of them. A card punched with holes, the position of the holes representing the value of numbers. Here you can see the holes laid out in a particular array on the card. Each position in the card can either have a hole punched in it or not, and so can represent a binary digit. Here's another card in which the information on the card is coded along the top in a printed form so that you can read it off more easily without having to look at the holes themselves. Here's another card in which, although it's not punched, the position of various types of information that can be represented on the card has been marked along the top. The card is especially laid out, in fact, for a particular job in which different parts of the card are devoted to different kinds of information. The other way in which we prepare information is in the form of punched paper tape, a long length of paper in which holes can be punched. In each position on the tape, we can either have a hole punched or not, and so again, each position on the tape can represent a binary digit, either 0 or 1. In each case, the numbers are coded as patterns of punched holes, and when it's ready for the computer, the cards or the tape pass through a machine in which the position of the holes are detected, usually by shining light through them and letting it fall on a photoelectric cell. And in this way, the pattern of holes becomes a pattern of pulses inside the machine. Modern machines can take in 1,000 digits or so a second in this way. Here we see a picture of cards being fed into a computer, and here's some punched tape which is conveying the results of a calculation which has been made to control a tape punch to produce the results in that form. But most of the results from a computer come out on a printer which can print as many as 1,000 lines a second.